So in this problem, we are given two bodies, M1 and M2, with position vectors R1 and R2 with respect to an inertial frame. We're deriving the two-body equations of motion. So we need to use this relation R equals R2 minus R1, and you can see that's simple vector math. And acceleration is R double dot, and we know that from Newton's second law, the force equals mass times acceleration. And then we can use Newton's universal law of gravitation. And then we can do, we can use Newton's third law to know what the force on mass 1 is. It's the same, but in the opposite direction. And then rearranging Newton's second law for R double dot, we can get this. And it simplifies to that. And for mass 1, it's the same thing, except we have M2 on the top. Then we can use the relation that we defined above to relate these two to find what R double dot is. And that simplifies to this expression. And we can call mu equal to g times m1 plus m2. So that simplifies to exactly what they wanted us to derive. Mu is the gravitational parameter of a body. This is a constant calculated by mu equals g times the mass of the body plus the mass of the satellite. And since the mass of the satellite is usually so small, it is negligible, and it's approximated to 0, thus allowing for the approximation of mu equals g mass of the planet. So in this problem, we're simulating a two-body motion using ODE 45 that propagates a spacecraft's trajectory around Earth. And it has the initial conditions of this position vector and this velocity vector. And we're supposed to plot the position trajectory of a single 3D orbit. So these equations are the fundamental equations that we need to use. And this is the MATLAB code that uses those equations. So as you can see, that's the position vector and that's the velocity vector. Then we have an initial state, which is y naught. And then we plug that into ODE 45 right there. That gives us the trajectory, and we plot it right there using plot 3 like they asked us. Now we need the mass-specific orbit energy, the scalar angular momentum, and the eccentricity. So we need this equation right here, that equation, and this one. So in the code, we can see that we need different tolerances for these equations. So we have a tolerance array, and we iterate through each of those tolerances, calculating H, E, and the energy. So we have the trajectory as well, right there using ODE 45. And in this first for loop, we are calculating H and the energy in E. And in order to do that, we need to do that equation, which is right there. And R cross V is right there. And the energy is right there. And then we need the function ODE func, which is used to find the trajectory of the spacecraft. So we need to differentiate the position and the velocity. So the position differentiated is just the velocity, that's why it's y4, y5, y6. And we also need to differentiate the velocity, which is in lines 97 through 99. That is the trajectory of the spacecraft, and these are the orbital elements at the specific tolerance, which is 0.001. And then the tolerances, the other tolerances give us the orbital elements behaviors as well. Now, in this problem, Luke Skywalker enters the system, and he's in a parking orbit and is observing this planet, which has this gravitational parameter. It has this energy and this angular momentum, And at this time, it uses its instruments to find that it has this position away from the center of the planet, and we need to find at T naught A E R A R P period and true anomaly. So first, let's find the semi-major axis, A, and this relation relates the energy to A, so we can rearrange for A because we know the energy because it was given to us, and mu because it was also given to us. So that is the semi-major axis in kilometers. Now we're trying to find the eccentricity, and this is a relation that relates it to both the energy and the angular momentum, which we both have. We have both of those from above. That gives us 0.12. Now we're trying to find the radius at perigee and apogee, and in order to do that, we need this intermediate term called the semi-lattice rectum. And now we can find the radius at apogee using the p and eccentricity that we just found. And now the radius at perigee is the same thing except you're adding the eccentricity. And there are many ways to solve for this. There are different equations that relate different terms, and you have a lot of knowns already. So there are a lot of different ways to solve for these things. And this is the period. We already found the semi-major axis, and we know mu. And that's in seconds, and then we convert it to hours. And to find the true anomaly, which is the position, the angular position of the spacecraft on the orbit, we can rearrange this equation for theta. We know that h squared over mu is p, and we know p. And just plugging in all of those, rearranging for theta, we can find that true anomaly is negative 0.775. And it's negative because it's moving towards perigee. Okay, so part B. Now we need to justify which type of orbit it is, what conic section. So since we know that the energy of the orbit is negative, elliptical orbits have negative energy. So it is elliptical. But we also know the value of E, it's 0.12, which is between 0 and 1. So that means it's elliptic also. Okay, so at part C, we find theta, which we already did, and then determine the velocity vector in its orbit and express in r theta h frame. So we know that the velocity in the r theta h frame is r theta h, so we can assume that it is a planar orbit and it stays in the equatorial plane, so the h component is 0, and then the VR equation is this, and we already found E, and h is this value, which they gave in the problem statement, right there. And E is 0.12, sine of theta, which we found above right there. This comes out to be negative 0.18. And for v theta, similar equation, and we know all of those values, and it comes out to be 2.3. So writing it in the form of VR, v theta, 0 for the h component, we get this. Now we want to draw a diagram of the satellite in the orbit in the specific location with the specific velocity and the key orbital elements on it as well. So that's the center of the elliptical orbit, that's the focus, that's the eccentricity vector, that's periapsis, and that's apoapsis. Half of the long end of it is the semi-major axis, and the short end of it, half of it, is the semi-minor axis. And then the distance from the focus to apoapsis is RA, focus to periapsis is RP. The distance from the focus to the orbit, that length, is P, and that's where mass 1 is. Mass 1 is at the focus, and the satellite is at a negative angle, so we can see that it's right approaching periapsis, very close to periapsis, with a v theta, which is positive, which makes sense, it's going up, and VR, which is negative, which makes sense, that vector is pointing down. In this problem, we're given the periapsis radius and the apoapsis radius of the satellite in this orbit, and we are asked for different orbital elements and information. So first it wants the eccentricity. We can find it directly from the radius of apoapsis and periapsis with this equation. And we find that it is elliptical, it's less than 1, greater than 0. And part B wants the semi-major axis. And in order to find the period of the orbit, the time it takes to get all the way around one cycle, it depends on this semi-major axis, and we just found that, so we can solve this. So that's about 35 hours. And the energy is this. And we remember that the energy of an elliptical orbit is negative, so that makes sense why the energy is negative. And now we're trying to find the true anomaly at this altitude. So we can use this equation. To find an intermediate value so that we can later find true anomaly. Okay, now we found the angular momentum, and we know that the conic equation involves the angular momentum. We found E, and we found H, so now we rearrange it for theta, and we solve. And the value for R is the altitude, which is Z, plus the radius of Earth, which is 6,371 kilometers. And that is R. So that is what you would plug into the equation in order to find that the true anomaly is 82.3 degrees. And in part F, it asks for the radial velocity and the tangential velocity, the tangential velocity is v theta, and the radial velocity is vr. And we can use these expressions to solve. And that's in kilometers per second. And then part G asks the speed at perigee and apogee. So VP and VA, we can use the vis viva with the radius of perigee, which they gave us. And the same thing, but with the radius of apogee, which they also gave us in the problem statement. So at apogee, it has a much smaller velocity, which makes sense because it's further away from the focus. And the last problem of this video is a meteoroid approaching Earth from very far away, and this is a hyperbolic orbit. So it asks us to find the eccentricity of the orbit, and we know that in hyperbolic orbits, it's going to be greater than 1. So they gave us a little bit of information. We know the radius, we know how far away the object is, and we know the true anomaly, which is 150 degrees. And we also know the speed of the asteroid. This is going to be useful when we need to use the vis-viva equation to find one of our unknowns. So in part A, it asks us for the eccentricity. We can use this equation. We also know that h squared is also equal to this. And then we can set those two things equal to each other. And the only unknown in that expression besides E is the energy. And the energy, we know the velocity, we know mu, and we know r, so we can find the energy. And then plugging in all of our knowns, and then simplifying into a polynomial equation. We can solve it for 2 values of E, and then we select the positive one to be the correct one. And then we need to find the altitude at closest approach. We know that altitude equals the radius of perigee minus the radius of the Earth. And we know that the radius of perigee is the closest approach because perigee is the closest to the focus, which is where the planet is. And then our expression h equals rp minus re, when we place h squared over mu in the expression for rp, we find that this expression is right here. And that simplifies down to this. And so the altitude is 5,087 kilometers. In part C wants the speed at closest approach, which is the speed at perigee. So we need to use the vis-viva equation. But we know that it is a circular orbit right there, so we can just simplify it down to this and use the radius of periapsis for r. And we find that the velocity at closest approach is this. Thanks for listening. Subscribe for more useful videos. to use. And